Okay, guys, time to do the PowerPoint. Okay, so I'm going to try to go quickly through the PowerPoint because I don't want to overly bore you today. Okay, so we have thermochemistry. Thermo, we know our parts. Thermo has to do with heat, thermos, thermometer, thermo has to do with heat. Chemistry, chemistry. So thermochemistry is the chemistry relating to heat. And look, it's the Hindenburg, which happened in New Jersey, by the way, just in case you're curious. And of course, that is definitely thermochemistry. We'll talk about that later, about exothermic giving off heat. And of course, fireworks in the backyard, obviously, barbecuing, and then, but wait a minute, this is like very scary and dangerous. This is kind of dangerous too. Don't want to catch your house on fire. So what are we going to do? Well, we're chemists. We want to measure things. So we do it inside something called a bomb calorimeter. Not because it's a bomb, but because you seal it up and it could explode, but it doesn't. Okay, so you have your sample. You put your sample in there. You put some oxygen in there, and you have the little lid on top, and you have a little stir. And what happens is, once you light it on fire, it catches on fire, heats up the water, and you can do a calculation, which we're going to talk about later, about doing these calculations. And if we had lab, we'd be trying to figure out how many calories were in a cheese doodle. But maybe I'll show that to you just because it's awesomely fun. Okay? So, what is thermochemistry? Once again, thermochemistry is the study of heat changes in chemical reactions. Thermo meaning heat. So, heat chemistry. Know your parts. Part of your words, which is good for your SATs whenever you get around to taking them sometime next year. Okay, now we have two kinds. We have an exothermic. Exo gives off heat. And I think we did a lab where stuff gave off heat. And I think we passed around my little hot hands or whatever. So something's giving off heat. That is exothermic, which means it transfers the thermal energy to its surroundings. And you are its surroundings. So it gives its energy to you. So exo, energy out. So if you look at the equation, which is important to know, so let's look at these equations. We have hydrogen and oxygen, which is what the Hindenburg did, and it gave off, actually the product was water, surprisingly, and a lot of energy. So this went really fast, gives off lots of energy. So the energy is on this side of the equation. It's a product. It's coming out. So the energy out is exo. So my wife likes to say exo is like hot, hot, hot. Hugs and kisses, X's and O's. So that's my wife's addition to my PowerPoint. Now, of course, I didn't think of that. I thought of it a slightly different way. My way of thinking it is exo being exo girlfriends, and they go out, 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 out. Exo, bye, bye, bye. So my exos are in Texo. Okay. Yes, your way or the highway. Okay, so we have endothermic. And I can't go on the highway because I'm not supposed to leave the house. So, endothermic is energy in. It absorbs energy. So, it's absorbing it from the surroundings. It feels cold. So, look, it's the same equations but backwards. So, here we have the energy going in. It's a reactant. Energy going in. So energy goes into water to separate that. Too bad we're not doing that lab in class. To make hydrogen gas and oxygen gas. Yes, you can actually split water into the elements. Takes a lot of energy. Okay, now here's an interesting one. This one's an energy of water going to water. But look at the little letters. S for solid, L for liquid. So we're going from ice to liquid water. So ice absorbs that energy from you. So that is why ice feels cold. It's absorbing the energy. It is endothermic. So important to know. Now let's take a look at Energy diagram. This is important. So we have a forward path. This loves to show up on AP tests. So whenever I see this on an AP test, I'm like, oh, this is easy. So forward path of the reaction. Here's potential energy. So let's take a look at this little guy. Here we have a car. A car is not a reactant. Well, just pay attention to the concept. Okay, so we have our car at the top of this hill. This is the height of the energy, technically from the bottom. So all the way up there is the energy, the potential energy of the reactants, or the starting of the reaction of 0. So it's starting way up here. So here's the car at the top of a hill. Now, there's a little bump at the end of the hill. So what the car does is puts a little energy, hit the gas and go up the hill, a little bit of energy in, and then down the hill really fast. So what is this bump? Well, this bump is called the activation energy. This is the extra energy needed to start a reaction. So, using a barbecue example, we have a barbecue outside. If you have a barbecue, it doesn't go by itself. You have to use lighter fluid and a match. That is the activation energy. You need to put energy in for it to go. Your candles don't just magically turn themselves on. You need to light them with the lighter. So that's the activation energy, the energy to start the reaction. Now, so we're going to be paying attention to the starting and the ending. For now, we're going to ignore the bump. For now, we're going to need to know that later. But for now, we ignore the bump. So we're starting from here. We're going downhill. It's going downhill. Car going downhill is giving off that energy. So that's going to be an exothermic reaction. But that's a car. Okay, well, here's another one. So here's another picture with little squigglies. So this one is something that you might see on an AP test or something, where you have the same reaction coordinate. Starting point is where the reactants are. Ending point where the products are. The height between the reactants and the products, which is where your car started to where your car ended, that difference is the difference, delta meaning difference, in the energy. So that's the energy of the reaction. But for it to do that, it needs to go up this hill first. On this picture, the hill's a little bit bigger, which is going to be important later. So this is the activation energy, the energy to start it. And what's way at that top is called the transition state. So you have a reactant or a bunch of reactants reacting. Once they come together and start reacting, they reach this transition state in the middle, which is halfway between a reactant and a product. It's got to go halfway in between. So it goes halfway, forms this transition state, which is high energy, but it can't stay up there. So it's going to go down the hill to make the products. So here we have more details on our activation chart. Okay, so back to the chart where the car was. This is the same one, except instead of a car, we have carbon. Get it? Carbon. Yeah, my audience is sleeping. So, just like you guys. Oh, you're not sleeping. Okay, my audience is watching videos on YouTube. Oh, just like you guys. Okay, never mind. I feel I know you're listening. I feel just like I'm at school. Anyway. Okay, so here we have carbon. Here we have oxygen. Exactly. You yawning. So the carbon plus oxygen, just like you're barbecuing your charcoal. It's made out of carbon. So it just all of a sudden doesn't burn. You have to give it that activation energy, the lighter fluid and the lighter and the match before it goes. Once you give it enough energy to start, it goes over this hill, it goes down, gives off additional energy. That extra energy, the exothermic, that extra energy is able to kick some more carbon down the hill, and more, and more, and more, until your barbecue is done and all you have is ashes sitting in your barbecue. So that's when all of the reactants are gone, and then you have products. So this reaction does go, but for barbecue, it takes a little bit of time. And we'll talk about rates of reactions later, about how fast things go. Okay, so here we have the thing with the car. notice where we're starting, notice where we're ending. This difference is the energy released. For now, ignore the bump. Start, end. Okay, so here we have the same thing without the bump, so it's not confusing. Reactants start, products bottom. The difference between the top and the bottom, the delta H, is the difference between the reactants and the products. It's going downhill, giving off energy. That is an exothermic reaction. It gives off heat, and that is what an exothermic reaction looks like. Exothermic reactions, I studied them before they were cool. Yes, it's a cat meme, and I've been told I need to show our actual cats on a video. So we will send that to you soon. Okay. Yes, we will do it, but not now. Okay, so here is an endothermic reaction. We have the same thing. We have the reactants on this side. We have the products on here. That little activation energy bump is gone, so you're not confused. So look, we're going from low energy to high energy, like riding a bicycle up a hill. So to ride a bicycle up a hill, you have to put energy in. Energy in is endothermic. Energy in is endothermic. So cold pack ice cubes, endothermic. The products have more energy than the reactants. So it's absorbing energy. Energy is going in. Got it? Good. Okay, so let's see if you really got it. Let's see. Which one is exo and which one is endo? Number 1, ignore the bump. Number 2, look at the reactants. Look at the products. This one's going downhill. From reactants have more energy than the product, so it's giving off energy. That's the delta H, the heat of reaction. That's the enthalpy. Nice vocabulary word. So this is giving off energy. So it's giving off, Aaron, gives off energy is exo or endo? Exo is correct. Good. Good guess, 50-50. Okay, and then we have the other one here. We have reactants going uphill. Ignore the bump for now. Reactants to products. If I was doing this in class, I'd cover my hand. I'm doing it right now, but you can't see it. I'm covering my hand over the bump. So all we're doing is looking at the reactants and the products. Ignore that. Reactants to products. We're going up the hill. So you're putting energy in. Energy in is endo. In endo. Exo. Got it? Okay, now, this one looks a little confusing because it's from an SAT practice test. Or, actually, I take it back. AP practice test or AP test. So, ignore this for now, but we're just looking at the curves. So, let's look at the curves. Which curve is exo and which curves are endo? Mr. G, they're not flat. I don't know where the start and where the end point is. This is the start. This is the end. Stop worrying about it. So we're looking at the start point to the end point. Ignore the bump for now. So this one's going uphill. Uphill is? I can't hear you. Uphill is? The other one, which is endo. Good job. Okay, so uphill is endothermic. You got to put energy in to go up the hill. B, look at that one. It's going down the hill. So down is exo. Okay, here's another one. This one also, it's got a big bump, Mr. G. Didn't I just tell you to ignore the bump? Ignore the bump. Start, end. Doesn't matter if you're going from school to the house, and if you're stopping at the Skylark, or if you're driving all the way, I don't know, all the way down to the movie theater way down Route 1. Doesn't matter which way you go to stop. It does matter that you start at school and got home. Start at school, and got home. Doesn't matter if you take the shortcut or the long way. So, starting here, going there, reactants, products, going uphill is endo. Going downhill is... Can't hear you. Exo, good, see? If a 6th grader could do it, you can do it too. Okay, so we're going down, and he's not even looking at the PowerPoint, just like you guys. So, look. So we have our point that we're ignoring. We're going downhill. So now we have our 2 exos and 2 endos. So which one is the most exo? Well, these are the 2 choices. Well, this one's got a bigger bump, Mr. G. Yeah, but didn't I say to ignore the bump? So we're going from here to here. This, reactants to products, is farther away than from here to here. So the further away they are on the energy, just like it was in the last unit with batteries, the farther they are on the energy chart, the more energy you get. So same with this one. The farther they are, the more energy comes out. So this one is the most exo. And which one's the most endo? Well, I'm assuming you guessed this one because it's the farthest from here to here. But Mr. G, this one's got a big bump again. Remember, from here to here. We're ignoring the bump for now. Okay. There we go. So, do a little bit more and then we're done. So we got the first law of thermodynamics. What does the first law of thermodynamics say? Do I have to memorize this? Not for my class, but you know what it is anyway. It's the law of conservation of energy. What does that mean? The total energy of an isolated system is constant. Energy can be transferred from one form to another, but neither can be created or destroyed. Do you have to write that all down? Hell no. Okay? You just need to know the bottom part. Energy can neither be created nor destroyed. That's it. You can only convert it from one form of energy to another. But Mr. G, what about E equals mc squared?
That's definitely not any person's voice.
Thank you. It does not apply here. This is the law of conservation of energy. Okay. So, and when I do my What the What Wednesday on Not Wednesday, you'll see a nice version of this. Go back. The conservation of energy. Energy cannot be created or destroyed. We have 2 forms of energy. So you guys taking physics next year are going to see this kinetic energy and potential energy. So kinetic energy is the energy of motion, and potential energy is stored energy. So we can convert potential energy into kinetic energy and kinetic energy into potential energy, just like we did in our other class last unit, chemical energy to electrical energy. Now we're converting kinetic energy to potential energy. And that has to do with these guys. So here's the dude on the bicycle riding up the hill that I mentioned earlier. So here at the bottom of the hill, we put energy in. That is energy in. You're converting your energy into potential energy. So your energy in goes to potential energy. So this is energy in. So now you're way at the top of the hill. You're all tired from your good workout. So now you're like, oh, I'm so tired. But guess what? I'm all out of energy. Well, you might be out of energy as the bicycle guy, but guess what? You have a lot of potential energy. Like Pinocchio would say, you have a lot of potential. I know all these people here with lots of potential. Yes, Pinocchio. So, you're at the top of the hill. You have potential energy, but no kinetic energy because you are so tired. But once you start going down this hill, energy out. So you're giving out that energy. So now you're going from potential energy to kinetic energy. Energy in, energy out. And notice, if you wanted to compare this chart with the other charts before, notice the starting point and the ending points are the same. How can that be? Is that exo or endo? The answer is neither. But you probably won't see that. Probably. Okay, so talking about energy, what is it? Let's see how much we got. Oh, we'll talk about food and that's it. Okay. Because all this bicycling is getting me hungry. So, energy, what is it? It's the ability to do work. That's a physics thing. Work is a physics thing. So what do you mean by work? Well, let's see. We got energy, we got solar energy, we got electrical energy, we got chemical energy. Well, look, we got wind energy there, we got natural gas energy there, we got nuclear energy here, and we got Big Mac. What does a Big Mac have anything to do with it? Well, the answer is everything, because this is not chemical. Well, I take it back. It is chemical energy. This is food energy. So when you eat this, you got lots of energy from eating the food. So if you were measuring things outside in, say, I don't know, chemistry lab, you might be measuring something in called a joule, which is a unit of energy. But of course, you don't care much about joules. You don't eat your joules. You eat your calories. So calorie is a dietary unit, and that's how it's measured, a calorie. Okay, so there's joules, kilojoules, calories, and we'll see in a second what a kilocalorie is. So yum calories. Getting hungry now. So what the heck is a calorie? Well, a calorie, notice the small c, is the amount of energy, not a typo, needed to raise the temperature of 1 milliliter of water by 1 degree. That's the definition. Do you need to know it? No. But that's what it is. So 1 milliliter of water is a very small amount. 1 degree centigrade, very small amount. So a calorie is actually a very small amount of energy. But that's a little c for calorie. When you look at the calories on food serving, it's a big C. A big C is not a calorie. A big C is really a kilocalorie. And what is a kilocalorie? A kilocalorie is 1,000 calories. So what's that? That says, it says 60 calories, means not 1 ml of water 1 degree 60 times. It's 1 ml of water 60,000 degrees, or the other way around, 60,000 milliliters of water, which is really 6 liters of water, 1 degree. So that's actually a lot of energy. So when you're eating a snack and you say, oh, it's only got 20 calories, Tic Tac only has 4 calories. Well, that's actually a lot of calories. But then again, when your normal day-to-day work, you have 98.6 degrees, if you don't have a fever, 98.6 degree normal body temperature. How does that come? It comes from your food calories. So your body is burning these calories by just sitting there. Now, of course, you can burn more calories by exercising, which we'll talk about in a minute. So as a scientist person, or if you're a food scientist person, they actually do this analysis to get the labels, or else the FDA will be on their case. So how much per serving? 60 calories. So how did they measure that? They put the stuff into that bomb calorimeter I mentioned earlier. You put your sample in there, you give it some oxygen, it's in water bath, you zap it, it burns, you measure the temperature, because temperature has to measure heat. So you're measuring temperature, so it gives off energy. Burning stuff is exothermic. The water gets hotter, and that's how you do it in the fancy schmancy science lab. Now, of course, in our fun chemistry lab, we would do it with a cheese doodle underneath a can of soda to heat up water, but that's what we would do. Okay, so same thing to figure out how many calories are in your cheese doodle. Okay, so how many calories are in food? Well, let's see. If you had 4, and we'll talk about these units are going to be important later in the next part of the PowerPoint. Carbs, 4 calories per gram. Protein, 4 calories per gram. Mr. G, what do you mean? Carbs and protein? They're the same amount of calories per gram? Yes, they are. But I'm on a diet. It's a low-carb, high-protein diet. It makes me lose weight. Yeah. We'll talk about that later. And then here we have fat. Whoa, 9 calories per gram. So for the same amount of grams, you get whopping 9 calories per gram, which is a whole lot more. Okay, so fat, you get a lot more calories, which is the problem about all these yummy foods up here with all that fats in it, because it makes you fat. Okay, so let's talk about, before we talk about fat, let's talk about energy from food. So, how do we get the energy from our food? We get it from breaking and rearranging the bonds in the food. So, we'll do the food on the bottom in a minute. But first we'll do the top part. We have hydrogen and oxygen, the two gases that we mixed earlier in the previous demonstration or picture on the PowerPoint. We react them, it gives off energy. Energy comes out to make water. So what you're actually doing is look at the bonds. You're breaking these bonds and breaking these bonds, and now you're making these bonds. And if we were in AP chemistry, I'd be teaching you all about the delta H's of each of the bonds. But guess what? You'll learn it in college when you get there. Okay, so you're breaking this bond and breaking this bond. So breaking 2 hydrogen bonds and then a double oxygen bond. And here you're making a hydrogen-oxygen bond here, 2 of them there, and 2 of them there. So you're breaking bonds and making bonds. And that is what gives off the energy, making bonds and breaking bonds. So we got glucose, which is sugar. We have oxygen, which is oxygen. We react those two together or burn them. Or in your body, you're burning calories. And yes, you are burning, but through a chemical route, not through like burning, not by fire, unless you're on fire, which is not a good thing. Okay, and your waste products are CO2, which you breathe out. Your cells breathe out your CO2. You also give off water, which you breathe out and pee out too.
Nice.
Yep, nice, and sweat too. And then you get 38 ATPs, if you remember that from biology. And if you had Miss Degg, she probably would have given that to you. So you're making 38 ATPs. That's the energy. Well, gee, I thought it was calories or joules or whatever. Well, guess what? This is biology food. So you get 38 ATPs and your body uses those ATPs to give you energy in your muscles and your brain. Okay, so I'll save that for later. Okay, so now that you know this stuff, guess what? Get to do the quizzes. And there's one thing that I didn't cover in here. The energy goes, heat energy goes from hot to cold. That is the transfer of energy. Because the next slide, I'll give you the slide right here. What is energy? The heat, thermal energy goes from the hot thing to the cold thing. It's transferring its heat energy or kinetic energy from a hot object to a cold object. Okay? And when you add the heat, the particles move faster and faster and faster and faster. And that is delta H, or change in enthalpy. Enthalpy. So delta H. So that has to do with the heat. So when you touch the pan, guess what? The pan gives the heat to you. Ow! But Mr. G, it's going to be really hot on the weekend. I'll turn the air conditioner on. When you turn the air conditioner on, doesn't it make it colder in the house? Yes. And no. Yes, it is colder in the house, but it's not really making it colder. It's actually taking the heat out. Where does it take the heat? It takes it to the outside. And if you feel the outside of your air conditioner, you'll notice it gets really hot when it's running. And also your refrigerator, which is a tiny little air conditioner in your house, your refrigerator and freezer, if you feel the outside of the freezer, and if your cat likes to hang out on the bottom, that's why, because it's nice and warm down there, because the heat's coming out. And it's pulling the heat out. How's it pulling the heat out? Well, that's a little complicated, but it's not. It's actually expanding a gas and a liquid, which we were mentioning before. So that's what's happening inside your refrigerator. So it's not really making it cold. It's actually taking out the heat. So in nature, the heat goes from the hot thing to the cold thing. That's the transfer of heat. There is no taking heat out, which is confusing, but it's the way it is. Or you can't make it cold. You can only take the heat out. Okay, and then we'll do all these nice calculations and things later. We'll worry about that tomorrow or next week. Okay, so do the quizzes and have a nice weekend.